far, all of our discussions of the solutions of the Schrödinger equation have been for one electron. In the case of multi-electron atoms, we talked about an effective potential represented by the nucleus and the remaining core electrons. But clearly this is very unsatisfactory, and much of the richness in quantum phenomena comes from taking into account the interactions between electrons. Physics graduate students know what pain is involved in finding wave functions to describe complex states like this, but happily the chemistry community now has at its disposal an absolutely wonderful tool grounded in work by Hohenberg and Kohn in 1964. The Hohenberg-Kohn theorem said the following thing: the ground state energy of a multi-electron system is a unique functional, and I'll explain that word in a minute, of the electron density distribution N of R. So the idea of a wave function, a complex probability amplitude, and all of the complexities associated with the wave function, at least for working out the ground state energy, could be replaced then simply by a distribution which told you what the electron density was at every point in space. No wave functions. The question is, though, this energy functional, and by which I mean a function of a function N of R, could be minimized to determine the energy. Now, this minimization is not regular calculus, and so I'm showing the condition for a minimum energy here with some symbols you're probably not familiar with. What this statement means is that we will vary the function N of R and find that function which minimizes this functional E of N of R with respect to variations in N of R. This is a subset of calculus called variational calculus. Happily, we don't have to know too much more about it because the results have long ago been worked out by collaborators of Kohn and are available as packages available for free distribution in many cases that are relatively easy to use. Now, this sounds like almost magic. The drawback is that this functional E of N of R is not known. And so the work of the density functional community over what is now nearly the past half century has been to optimize functionals for particular problems. The Hohenberg-Kohn theorem proved that such a functional exists, but like the Holy Grail, it has never been found, and there's a Nobel Prize waiting in the wings for the folks that do find the true functional. However, here is an example of a rather old functional. It's not one that's in use today, but I chose it because the terms are sort of easy to understand. So let's go through them one by one. Let's begin with this first term here. For a free electron gas, and in Chapter 7 we will talk about free electron gases, it's fairly straightforward to show that if you have a uniform electron density in a free electron gas N, the average energy of the electrons is given by n to the 5/3. So what's been done here is to say, let's say that the same applies to a distribution that varies over space. So this is the kinetic energy term. course integrated over space to give the total energy. The second space as term you'll recognize quite simply as the Coulomb energy, just the density at point 1 times the density at point 2, multiplying by dr1 and dr2 to get a charge out, and then divided by R12, that's Coulomb's law. So this is the electrostatic interaction. The next term is the nuclear potential. I've just shown it here as the electron density times some potential. The choice of this potential is actually quite critical, and one avoids a lot of complications by ignoring the core electrons by choosing something called pseudo-potentials. The last term is a somewhat mysterious term called here XC for exchange and correlation. One of the difficulties with many electron wave functions is because electrons are fermions, you have to make sure that when you exchange any pair of electrons over any distance, you change the sign of the wave function, if you remember our discussion at the beginning of Chapter 2. Then there are effects that are not included in any of these results derived from the free electron gas, and they're lumped into this term too. In this case, I'm showing you one very simple approximation to this. Debye showed many years ago that for a free electron gas of uniform density, exchange and correlation terms could be represented by the density to the 4/3, and in this functional it's replaced now with just a function of position. So, with this functional known then, a computer program can be written to explore for functions n of r that lower e that you calculate using this functional. There turns out to be a quick route to doing this, but really one doesn't need to know it. I show you here a calculation of the charge distribution on a very complicated molecule, a molecule that would be almost impossible to solve by conventional methods, done very quickly by density functional theory. I use it all the time in my research. It's a tool that works a lot better than it should do, given the constraints that it's restricted to calculations of the ground state energy, but it's made quantum mechanics something you don't have to be quite so scared of. So I hope for the remainder of this book you'll think of quantum mechanics as your friend and ally and not too much of a mathematical beast.